the MC, and I'll be with you for the start of this discussion. It's my great pleasure to welcome you to the MLPerf training briefing for the press and analysts. As a reminder, this is under embargo until June 4th at 8 a.m. Pacific time. We'll be recording this meeting, and then at least the first half of it, not the interactive Q&A, but the first half will be processed and then made available to all of the attendees. If we want to go to the next slide. Thank you so much. So as per usual, we have a lot of briefing material that we've shared ahead of time, including the results, the supplementals from all of our fantastic submitters, the press release, and then the recording will be uploaded in this Google Drive as well. Now, this time we did something a little bit different. We have a new benchmark. We'll be talking about that in turn. The blog for that benchmark actually went out a few weeks ago. So I think the link is included in this slide deck, and this slide deck will also be shared through Google Drive. So next slide. So we're, I will be doing the welcome, and then our chairs, Shreya and Hiwat, will be taking us through the overview of sort of what's new with the benchmark, as well as some details on the new benchmark in the suite, and then followed with Q&A for all of the submitters. Next slide. Just as background for those who aren't familiar, MLCommons is a nonprofit. We are an industry consortium that brings together academia, our friends in industry, and increasingly civil society and a broader constituency, all focused around how do we make AI better for everyone, where better means faster, more capable, more energy efficient, and safer. So we have over 125 members. We're getting close to 90,000 performance results within MLPerf, which is a great number. Excited that for when we'll hit 100,000, hopefully, I don't know, maybe this year or next, we'll see. And the MLPerf benchmark suite has really expanded significantly to include not just training, which is our first and original benchmark, but inference, which is increasingly a focus, storage, edge systems like mobile devices and PCs, and specific verticals like automotive. And then our friends in AI Luminate have a benchmark that's actually focused on sort of AI risk and reliability as well. And one of the other things that we really specialize in and is very synergistic with a lot of the things we do is our work on data. You may not know, but we've done 4 or 5, fairly unique data sets that most of which have been released publicly. Data is one of the things that is absolutely critical for building these benchmarks, and it is the life's blood of AI. Next slide, please. All right. So, as a reminder, MLPerf is a benchmark that measures the speed of AI, and it is a full system benchmark. And so here we'll be talking about training. And I think some of the key principles that I think it's good to focus in on that we do and deliver with MLPerf is we want the performance to be reproducible, right? So we want that whatever we see from our submitters to be something that customers can achieve. And actually everything is structured in a way so that, many of the artifacts are there and everything is peer reviewed to get that reproducibility and reliable performance. We want the representative workloads here so that as we're going through and optimizing and, we see all of our members tweaking and tuning, large scale and small scale systems, optimizing software, all of those benefits accrue to the broader community, right? Because um, everything is reproducible, because we have our results in GitHub. Any customer can go in and sort of look at what's been done and say, oh, I can use that trick. And when these are all representative workloads that are indicative of valuable use cases that represent what's being done in practice, that means that the work we do here is not just for us, but for the whole community and really extends those benefits to everyone. It's transparent and fair, right? This is an open industry standards process. We have, very broad participation, and that's critical to ensuring that these benchmarks, not only are they fair and useful and valuable, but they are truly a level playing field for everyone, right? And that's super important. There's a lot of work and thought that went in to making these benchmarks approachable for anyone, regardless of architecture or approach. And you can even see that today. We've got folks who are participating from silicon providers to OEMs to CSPs to even companies that produce networking accelerators. So, and of course, AI training is an extremely expensive project, right? State-of-the-art training can cost a considerable amount, but part of our challenge is making sure that this is actually quite affordable. So, we want to take off a small piece of the training workload, not the whole thing, to give sort of a representative experience. So the goals of the benchmark, if we want to go to the next slide, please. Now, one of the things that's really beautiful about MLPerf is it's a full system problem. And is one of the most pressing, if not the most pressing application area today, when we go as a community to accelerate AI, we have a lot of different levers to pull on. And these are all things that our benchmark helps to measure. Right. Performance in MLPerf is driven by, the underlying silicon. Newer process technology will give us better performance. New architectures, optimizations in software, simple, better compilers, better drivers, data. Using new data types, for instance, can oftentimes result in smaller and more efficient neural networks, and quicker time to train, better algorithms, better networking, right? And that's something that we're seeing increasingly important, this round, without stealing too much of the thunder. We've seen more scaled multi-node submissions than we've ever seen before. And that means that the network and the configuration of the network and the algorithms used to map the problem onto the network become more significant. And of course, power varies significantly, right? Different accelerators, different processors have different power levels and allow us to devote more power to AI, which can often be more energy efficient ultimately, right? And that is one of the limiting factors. We see people talking about, gigawatt scale data centers, right? Power is incredibly important here. Next slide. And so, I think the key point is, MLPerf is here to give us those benchmarks, to measure all of these things and help chart the progress of the industry. So I'm thrilled to get to introduce this. I'm also extremely thrilled to congratulate our 20 submitters. So we've got 20 submitters this round. If you've seen the results for members of the press and analyst community, you know who they are. We'll get to call them out in a little bit. And I think at this point, it's my pleasure, I believe, to hand this over to Shreya, right?
I'll come in a moment. I think Hiwat will take over first.
Oh, okay. All right. Hiwat, you're on mute.
Oh, yeah. Okay. All right.
Take it
So
away.
yeah, hi everyone. I'm Hewitt. I'm one of the co-chairs for MLPerf training. So in MLPerf training, when in our benchmarks, we focus on measuring performance, which is like how fast can we train a model to some target quality metrics. And then the second thing that we measure is power, which represent the power consumed by all compute nodes and interconnect network and so on. Next slide. All right, so in MLPerf training, as we seen in this graph, so compared to Moore's law, we would have, if you go to the next slide, around 5x improvement in for that one. Maybe David, you can also describe more about this.
Oh, yeah, sure. Happy to hop in. So, one of the things that I like to do, and this is, an increasingly challenging bar to meet, but to ask ourselves, in the world of technology, right, a lot of us have become accustomed to Moore's Law. And that it sets a pace for the whole industry. We always expect that things get faster and cheaper and so forth. And that's really driven by Moore's Law. Now, it's slowing down a bit. But, I think one of the things, if you go back to some of my earlier slides, where I talked about all the levers we can apply, we should be doing better than Moore's Law. And that's actually one of the things that we very much see here. Right. And so the slides here, what this is showing is this is all of the benchmarks that are active in our suite and how they're doing relative to Moore's Law. And one of the things I want to point out here is this is actually setting a pretty high bar. Each point on here is the best performance for that benchmark in a given round. Sometimes that's, 64, 128, 4,000 processors, right? So these each individually are extremely hard benchmarks, right? It's not uncommon that you might see comparisons in marketing that are really posting something that's unoptimized versus something this is optimized. No, this represents, how good is the best getting over time. And what you can see is that through the combination of those factors that we mentioned before, silicon, architecture, algorithms, scale, everything, we're outpacing Moore's Law, especially on some of the most pressing workloads of the day, things like generative AI. Back to you, Iwat.
Sure. All right, so when we go to the results overview, so this round we're excited to have 201 performance results from 20 submitting organization. We also got 4 power results from Lenovo. So we also would like to congratulate new submitters. So we have first time submitters, AMD, IBM, Mango Boost, Nebius, and SCI TIX. Next slide.
And we also got right the power submissions from Lenovo.
Yep.
Yeah.
Yep.
I think one of the things to call out here is, we added in MLPerf power relatively recently to training. It's actually pretty difficult to do for these large at scale systems. And so we really do appreciate, the organizations that have gone out to measure power consumption for MLPerf training.
Right. Okay. So an MLPerf training submission. So we have closed division, which is equivalent on a closed model, which we'll have equivalent model data and so on. And then we also have open division, which is more relaxed, and you can change things like doesn't have to be mathematically equivalent. So in this round, all of the results we got were available, and we have submissions available on cloud and then available on premise as seen here. Next slide. All right, next slide. All right, so and now let's look at the benchmarks we have in 5.0 submission. So in 5.0 submission, we have 7 benchmarks that represent a wide range of AI workload domains that are important to the industry. So we have the benchmark here. So one of the benchmark is just to give a highlight is recommendation model training, which reflect real world applications such as ads, social media, and so on. And this benchmark is based on the LRM v3 model. And then second, we have large language models, which represent very important tasks such as text summarization, translation, question answering, and so on. So in MLPerf training, we have both pre-training benchmarks and fine-tuning. So on the pre-training side, which is like training model based on starting from like random weights and training on unlabeled data, we have BERT benchmarks based on BERT model, and then Llama 3.1 405 billion, which is a new model we added that replaced GPT-3. And then we also have fine-tuning model with Llama 270B with LoRa fine-tuning technique. And then when we go to the vision domain, we have object detection based on RetinaNet model. So RetinaNet is a one-stage detector that detects and classify objects. And then we also have stable diffusion V2 based model to evaluate text to image generation, which is right now a very rapidly growing field. And then finally, we have benchmarks for graph node classification, which can be used for like fraud detection, drug discovery, which is based on the RGAT model. So as seen in the table here, for each of our benchmarks, we specify training quality matrix to define when to stop training. And then we also have representative data set to ensure that our benchmarks accurately capture real-world use cases. Next slide. All right. Oh, and next, let's talk about what's new this submission. So in this round, we have a new benchmark, as I said, was Llama 3.1 405 billion. And then in this round, we also saw like a variety of new accelerators and then CPUs. So this shows the growing in diversity of AI training. So as seen here, we got submissions from AMD with ML 300X and 325X. We also got submission from NVIDIA with GB200 with Blackwell GPU, and then Neoverse V2 Grace CPU. We also got submissions with Granite Rapids, Intel's Granite Rapids, and then AMD's Turin. So we also saw so last round we had submissions with preview that moved to available, which is NVIDIA Blackwell GPU and then Google's Trillium. And then, as we said, we also got our third power submission from Lenovo, so which highlights that power efficiency is becoming one of the most important aspect of AI training, and like we're very excited to see this, and we hope that this will grow more in future rounds. Next slide. All right, and now let's look at the new benchmarks, which is Llama 3.1 405 billion pre-training benchmark. So which replaced GPT-3. So over the past couple of years, our GPT-3 benchmark has been successful in driving significant optimization efforts, and we've gotten very large scale submissions, but GPT-3 been around for more than 2 years and it's on the older side. So we wanted to replace it with a more current, more representative benchmark. So we use Llama 3.1. And the reason behind this is, one, it's a very popular model with around like 1 billion download in overall Llama models. And it's also openly available, and in addition, it's also matches the rapid adoption and the increase in capability of large language models such as like Nemotron 4, GPT 4.5, and so on. So the Llama 3.1 also have newer algorithms such as group query attention, rotary positional embedding, and so on. So if you want to read more about this benchmark, you can look at the blog we linked here. Next slide. Okay, so developing this benchmark was very challenging for the task force. So when we are developing benchmark, we have to find a stable benchmarking region where the model quality improves and there is a minimum run-to-run variance. So to find a good benchmark region and to develop this, we took 41K GPU days. So to compare for the Meta release Llama model, they trained it on 80K GPU days. So you can see that it was very like compute and resource intensive, and it was very challenging to develop. But the challenge is not just for developing. It's also very challenging for submitters because we scaled the model parameters by 2.5x, and we have 4x increase in context lengths, and then there's 3 times as many tokens to train compared to GPT-3, so which will significantly increase like memory compute requirement, which will create challenge for submitters. So, but one thing is, despite all this challenge, in its first round, we were very happy to get 14 submission in the first round. Next slide. All right, so to come into details about this benchmarks, so for the data set, we chose LANAI's C4 data set, so which is the same data set that we use for GPT-3 as well. So, so this is to make it easier transition to submitters. And then the other thing to note is, so when we build GPT-3 benchmarks, so we started from random weights and we pre-trained the model to custom stable checkpoint where submitters were required to train starting from. But when we come to Llama 3.1, we weren't able to have the same strategy because it was not feasible for us given the size and the complexity. So instead, what we did is we started from the Hugging Face checkpoint, and instead of using the tokenizer that they use in Llama, in the Llama paper, we used the Mixtral 8x22B tokenizer. And so we did that so that with new tokenizer, we force the model to train as a pre-training from the C4 data set. So this is our new benchmark, and I think Shreya would take this after this. Thanks.
Thank you, Hibat. That was really helpful. So the thing that I want to talk about is our results itself. This round, our results were pretty amazing. So looking at key insights, first, I want to talk about the volume of the results that we got. And we got lots of submissions this time, which is great. So if you just compare that to the last 2 rounds that we've had, so 4.1 was in October 2024, 4.0 was May 2024. In each of these rounds, we got somewhere around 150 to 180 submissions, whereas this time we got around 200, to be specific, 201 exact submissions. So we've seen like an increase in the total number of submissions, but along with just the total number of submissions increasing, this increases across the board, which essentially shows that all of our benchmarks in the benchmark suite are all really important workloads. And these big orange plots on our bar graph here, those are basically the number of submissions in 5.0. And the other 2 are like the last 2 rounds. So you can basically see that generally the orange is towering everything else, which shows that pretty much for all of our benchmarks, you see that there are more submissions this round versus the previous one, except potentially RGAT, which saw 1 less submission. But if we don't look at that, it's a pretty good understanding of how our submissions across the board have increased over time. And if you look at like even the Llama 3, the benchmark that Hibat just spoke to us about, even though it is massive, it is challenging, we still see a lot of submissions for this benchmark as well. Yeah, can we go to the next slide, Lori? Thank you. So Specifically, within the within the benchmarks that we got, if we look at just the Gen AI benchmarks and try to understand what the momentum is around those, we'll see that, so for Gen AI, we basically are considering Stable Diffusion, the Llama 270B LoRa model, and GPT-3 in the past, but Llama 405B now. So these are our Gen AI models. And if we just look at the momentum around those ones, we see that there's an even larger increase in number of submissions there, essentially showing that there's a lot of value in these benchmarks. Putting numbers into this, basically we saw around 50-ish submissions in the Gen AI area in 1 year ago, but right now we're close to about 100, specifically 96 submissions in the Gen AI. So it's almost double compared to exactly about a year ago. And if we look at just the Llama 270B LoRa, that one did really well. We saw almost 2x number of submissions this time. So just compared to last round. My take on why that might be the case is that this is a very current, important Gen AI workload, but it's also easily accessible. So we got submissions from lots of submitters for this benchmark because you can run it at different scales. And LoRa fine-tuning is one of the most common ways of fine-tuning even today. Yeah, can we go to the next slide? So that was about the volume or the quantity of submissions. There's also a lot of quality in our submissions. So they've improved, the performance improvements are pretty significant. The plot here essentially is the time to train for each of these benchmarks. And for training, the lower the time to train, the better the performance is. And you can see that the little bars for 5.0 are all much shorter than the 4.1. 4.1 was, again, our submission round last year around October 2024. And we see about 1.5 to 2.3x increase in the performance improvements if we're just looking at the 8 processor system submissions. So essentially sort of like one node submission scales across all the benchmarks. We see pretty good increase in performance improvements. And again, calling out the key performance indicators here would be Stable Diffusion and Llama 270B LoRa. Both of these see more than 2x increase in performance at this scale. But this round, it was not just that we got a lot of 8 processor submissions. We also got a lot of submissions of a much larger scale. So we saw a lot of multi-node submissions. Could we go to the next slide, Laurie? Thank you. So for this, what we're looking at is, actually, I think I see a question from Ray. So here we're talking about GPU processors. So yes.
Hold on one sec. So the question, just let's repeat it so everyone can hear it. Ray asked, for processors on this slide, can we go back to the last slide actually? Just so people see the in context. You know, what are we talking about here? Is it CPUs, GPUs, sort of broadly speaking, what's going on? And so one of the things I want to be clear about here is, you know, MLPerf is a full system benchmark, and you can train on a wide variety of things, right? We have submissions that train on CPU only. We have ones that train primarily on accelerators, such as TPUs, GPUs, all sorts of different things. So here in general, what we did to come up with this comparison, and you know, we said 8 processors. In this case, these are primarily 8 accelerator-based systems. And so the number of CPUs may vary between them, but what we looked at was sort of, hey, best 8 processors in 4.1 versus 5.0, right? And, you know, performance can vary. And, you know, here what processor really means is the processing element that does most of the ML computation, right? So even with, you know, an accelerated system, right, some portion of the computation is going to be done on the host processors, and some portion may even be done in the networking as well. So, right, you know, in reality, these are very complex heterogeneous workloads, but processor here is sort of the thing that does most of the computation. And if you go and look at these results, you know, we've got them in the footnotes here. Most of them you will see are accelerated. Does that answer the question, Ray? All right, I'm going to assume that's a yes. Back to you, Shreya.
Thanks, David. Yeah, that helps. So yeah, this slide is about larger systems. So here we were trying to explain how even at larger scales, as David was talking about larger systems, I'll say, we've seen significant performance improvements. So just to understand what this looks like, we have larger number of accelerators and hence a larger system, larger interconnect, and there are a whole wide range of submissions that we have. We picked out these two specific ones, these two cases that we have in this chart, where we're comparing 5.0 versus 3.1. 3.1 is the 2023 benchmark. And the reason we're looking at 5.0 versus 3.1 at the specific 64 processor scale is because we got these RetinaNet and Stable Diffusion results this time, and the most comparable results to that at the same scale was in 3.1. So that's what we're comparing against. And if you look at that specific comparison, we're seeing about 1.4x increase in RetinaNet to a 3.7x in Stable Diffusion. So this essentially reflects the complexity of scaled training. So it isn't, as David was talking about, not just like the CPU or the GPU or the TPU, but it's about the entire system. So it is networking, it is data, it is a scale itself, it's power, it's everything put together. Yeah, can we go to the next slide?
So we have a question here from Russ and a comment. So, for MLPerf, if you go back, actually, the metric for performance is time to train. And right, it is a run to completion benchmark. Yes, it is denominated in minutes, which, as Russ points out, has a slightly unfortunate characteristic that it is it's base 60, not base 10. So just something to be careful about in here. And the other point I want to make here is one of the real challenges with MLPerf, and this is a reflection of the underlying reality of machine learning itself, is we change our benchmarks quite rapidly. It's actually something that most benchmark suites don't do. And we'll get to talk about that in a minute. We already talked about that, how we, switched from GPT-3 to Llama 3.1, right? Just after a couple of years. That's not an unusual cadence. It does make these backwards comparisons a little bit challenging. And so, what we really did to make this comparison is we said, hey, for 64 processors, what's the best that we saw previously? And it happened to be that it was from 3.1, not one of the more recent results. So, this was not cherry picking in any way. This was us trying to come up with the best comparison to really illustrate what's going on.
Yeah. Yeah, and then to add to this, I would also like to say that this time it wasn't just these specific results at 64 processor scale, but we saw a lot of results that were submitting at large scales. And at large, I'm saying anything greater than 8 processor. I'm using that term a little loosely, but if we look at it like that, you can see that there have been a lot of submissions at that scale. And this is from a lot of different submitters, which is also very important. So once upon a time, there were very few industries that had large-scale systems available, and that was submitting using that to MLPerf. This time, it's different. There are a bunch of submitters, so it shows that the broader community is looking at like large-scale training, and a lot of cloud providers are also offering this to their customers. So it essentially says that large-scale training and large model training is now up for grabs for everybody. Okay, going forward, can we go to the next slide? Yeah, so these key insights that I just spoke about, the question comes up about, why we're seeing such great performance results in 5.0. And our understanding of why this might be is the new processors that we've got, the ones that Hibbert mentioned early. So we had like 6 new available processors. We had 2 that moved from preview to available. We've also, as I said before, seen an increase in the multi-node submissions. And then there is obviously more software optimization, algorithmic techniques that are improving, and lots of focus on advanced networking. So these are some of the reasons why we're seeing some great performance gains. And as always, it's also because MLCommons is putting a lot of effort to keep up with the pace of the industry. So if you look at our suite right now, 3 out of the 7 benchmarks we currently have are Gen AI workloads. We also have the Llama 3.405p this time. And we also have benchmarks that represent key tasks that are very important in the industry right now: recommendation, vision, text, multimodal, and graph applications. Also, we're continuing to strive to add new benchmarks that are relevant and important. So look out for the next round. With that said, I will hand it off to David.
Yeah. So as you go and look at the results, just, something I want to stress is that every one of these results, especially the multi-node ones, right? Many of them are using dozens of processors. They all represent a very significant investment of work by our submitters. Each one is a point of pride, no matter how small or how large. Uh, and so there's something that is behind each one of them. And, we have the supplementals to help our submitters tease some of that out. The supplementals follow the standard MLCommons rules, which is, no explicit or implicit comparisons really allowed. We want to allow our friends in the press and analysts community to do those comparisons. And of course, our partners the rules are different in their private briefings. But as you look at those submissions, look at some of these dimensions on which things are the same and how they're different, right? One of the things we talked about some comparisons earlier where we wanted to make sure they were the same system scale. That's really important because the techniques you use to compute with, say, 10,000 processors and 2 processors or 8 or 16 are often quite a bit different. The stress on the network is different. The workload becomes quite different in the parallelization strategies. You can see scaling over time as Shreya and Hiwat had mentioned, we're seeing processors going from preview to available. And it's not uncommon that performance may change as those things happen, right? Software gets better, bugs are, removed in the system or the silicon, right? You can also see submissions that use new and interesting software, new and interesting accelerators. For example, some of our submitters have proprietary SmartNICs that help accelerate at scale system performance, right? And so you can look at many of these differences and find interesting things hidden within there. So please take a look at the results. We do try to give them to you ahead of time. And I think then that brings us to questions for our submitters, and also a big thanks to all of our submitters, especially our new submitters, which, going from memory, right? We've got AMD, Mango Boost, Cytix, and Nebius. We always love to welcome, and IBM. It's always a pleasure to have more people come and join the party. So now